Good morning, students. Today I am going to take classes on classical mechanics, recap of Newtonian mechanics was done in the previous class, and in that class also we have seen how a charged particle in an electromagnetic field will move first in uniform electric field, then in uniform magnetic field, then in cross electric field and magnetic field, and finally in the field magnetic field where there is variation of magnetic field position. That means magnetic field gradient. Today we are going to discuss about recap of in your syllabus, recap of Hamiltonian and Lagrangian formulation. But I think recap will not suffice for you because you have not read these things in your previous classes. Because in first year mechanics you did not knew about know about the Hamiltonian and Lagrangian. Actually, Hamiltonian and Lagrangian formulation was there, but not in mechanics, but in mathematical physics, perhaps in third semester or fourth semester. And I guess you have you have not learned those things. So I will discuss Hamiltonian and Lagrangian formulation in detail, not only detail. Now, in order to understand Lagrangian and Hamiltonian formulation, you need to know what new physics is there. There is no new physics. Newton's second law of motion is the basic equation for mechanics, and there is no new law. But one shift is there. What is that? In Newtonian mechanics, we are dealing with forces, right? Which is a vector quantity. So you need to consider the directions. But you know, for conservative forces, force is derivable from scalar potential. You know from your first year mechanics classes. So if force is derivable from scalar potential, then we can deal with potential, right? Potential energy. In fact, Lagrangian and Hamiltonian formulation, energy is considered. Since energy is scalar quantity, it has no direction. So there is an advantage that we don't have to consider individual, consider the direction. In addition to that, the equation of motion for a single particle, Newton's equation, second law of motion, I mean Newtonian approach is more accurate. But for a system of particles, that means having a number of particles, it is very difficult to track the forces, different forces. But in Lagrangian and Hamiltonian formulation, the equations of motion for all the particles will be similar, provided we consider generalized coordinate. So first we have to consider what is generalized coordinate. Right? So first we have to consider generalized coordinate. Now what is generalized coordinate? In order to understand generalized coordinate, you need to know two other things. One is degrees of freedom. degrees of freedom, and the second is force of constraints. Force of constraint. First, I will discuss degrees of freedom and force of constraint. Then I will go to the generalized coordinate. Now, what is degrees of freedom? Now, as the name suggests, degrees of freedom is the how much degrees of freedom of particle. Suppose a particle is constrained to move in a straight line, then its degrees of freedom is one. If it is moving in a plane, its degrees of freedom is two. If it is moving in a three-dimensional space, then degrees of freedom is three. In general, a free particle has 3 degrees of freedom. One particle has 3 degrees of freedom. And if there are n number of particles, then there will be total in the system total 3n number of degrees of freedom. Right? Now, what are the force of constraint? Force of constraints are the restriction imposed on the system. For example, you are considering the motion of a simple pendulum, right? Its motion is actually in two dimensions, right? If you consider the vertical direction as the y direction and horizontal direction as the x direction, then its motion is in xy plane. So its motion is two dimensions. But there is one constant. What is that constant? Constant is that the length of the string from which the bob is the length of the string from which the bob is oscillating is fixed. So one constraint condition reduces the degrees of freedom by one. So actually the degrees of freedom of the particle is one. So force of constraints basically reduce the degrees of freedom. So suppose we have force of constant we denote it by F. F is the force of constant, number of constant that is applying on a system. For example, suppose we are considering motion of three particles, right? There is three particle system. One particle is there, one particle is there, and one particle is there. Then how much the degrees of freedom will be for this system? Degrees of freedom will be 3 into 3, that will be 9. But if you restrict the condition that the distance between these two, these three particles are fixed, then the force of constraint becomes 3. 1, 2, and 3 force of constraint is there. So degrees of freedom will be 9 minus, sorry, it will be 9 minus 3 equals to 6. So force of constant is basically the restriction imposed on the system. So for a three particle system, actual is degrees of freedom is 3 into 3 equals to 9. It is moving in a three-dimensional space. But if we impose further restriction that the distance between the three particles are fixed, then there are few conditions by which you can state this and each condition means the relation between say number one number this number one square number two square. So position coordinate between there is a relation between the position coordinate between one and two. So the one position coordinate can be expressed in terms of the other position coordinate. That's why degrees of force of constant reduces the degrees of freedom. So now the generalized coordinate. Now we consider generalized coordinate. Generalized coordinate is the any set of coordinates, any set of coordinates, coordinates that has set of coordinates that has minimum number of independent coordinates. Any set of coordinates that has minimum number of independent coordinates by which the system can be described completely. These are called generalized coordinates. Completely are called generalized coordinates. So in this example, say if there is the 3n degrees of freedom and force of constant is f, so number of generalized coordinate will be 3n minus f. This will be the 3n minus f. This will be the generalized number of, say, this is k. This is the number of generalized coordinates, right? Another thing is that in Newtonian mechanics, we have considered the position coordinates as the generalized. In most cases, position coordinate, which is basically has the dimension of distance. But in generalized coordinate, it need not to be position coordinate as the generalized coordinate. It may be angle, it may be you can see that it may be velocity, even it may be velocity, or it may be momentum also. Right? So I am now giving some examples so that you can understand the concept of generalized coordinate. First, I have to erase all the things. Now, examples of generalized coordinate. I am considering examples. Again, the classic example is I am taking simple pendulum. Simple pendulum is the classic example for any mechanics, whether you are considering Newtonian or Lagrangian or Hamiltonian or even in quantum mechanics. Right? So this is simple pendulum. Right? Now, if you know this axis to be minus y axis and this to be x axis, then there are actually 2 degrees of freedom, x and y degrees of freedom. But there is one constant condition, and the constant condition is that L, the length of the string, is fixed. L, the length of the string is fixed. So there is one constant. So here the xy coordinate can be reduced into x or y, but the generalized coordinate will be theta. So theta is the generalized coordinate. Generalized coordinate. theta is the angle, so angle may be generalized for it. This is example. Second example I can give you. Second example, particle on the surface of a sphere. Suppose there is a particle moving on the surface of a sphere. So what will be the generalized? Suppose this is the sphere, right? There is a particle. There is a particle. It is moving this way, or it can move this way. So what will be? This is the center. So what will be the generalized coordinate? Because the distance r is fixed, it cannot be generalized coordinate. So the generalized coordinate will be, suppose you make a fixed direction, this is theta, and other angle, that means you can go, this one line is there, the line is also this side or that side. So theta and phi will be the generalized coordinate. Theta and phi, this will be the generalized coordinate, right? Number three, I can give you another example. Say double pendulum. Double pendulum. Double pendulum. You know double pendulum? Actually, two pendulums are there. L1, L2, say L1, L2. So what will be the degrees of freedom? What will be the generalized coordinate? If I make angle with vertical, then theta 1 and theta 2, these are the generalized coordinate. Theta 1 and theta 2, these are generalized coordinate. Here theta and phi is the generalized coordinate. For a double pendulum, the angle the balls make with the vertical direction at the generalized coordinate. Now, another example, a classic example, I can give you a classic example of generalized coordinate. Particle in a central force field. Suppose particle in a central force field. Number 4. Example. Number 4. Central force field. Since the forces in nature are central, right? So particle in central force field, and since though it appears that the motion is in three dimension, but actually in central force field, you have seen in your first year mechanics classes that the particle is constantly moving in plane because it is acted upon by a central force. So there are two degrees of freedom. So the generalized coordinate will be r and theta or xy can also be, but r theta will be most convenient for central force field problem because there is symmetry. And the last example I can give you, the last example that I can give you is the suppose a cylinder moving down an inclined plane. There is an inclined plane, and a cylinder is moving down an inclined plane. There is a cylinder moving down an inclined plane. Then what will be the generalized coordinate? Right? The generalized coordinate will be theta, not this angle theta, not this angle theta. The angle the cylinder, a particular radius vector of the cylinder makes, radius vector of the cylinder makes with other is the called. So theta will be the generalized coordinate. Right? Now if it is a disk, if it is a disk, then the since the a cylinder can move in one direction, but a disk can move in two directions. So there will be 2 degrees of shape for a disk moving down an increase. Right. But for a cylinder, there is only 1 degree of freedom, so it will move. It has it is generalized coordinate theta. So I guess the concept of generalized coordinate is clear to you. Now with this generalized coordinate, so again I repeat, the generalized coordinate is the minimum number of independent coordinates. Right? Minimum number of independent coordinates by which a system can be defined completely is called generalized coordinate. Right? So two things are important. This is generalized coordinate are the minimum number of coordinates. That means we are considering the force of constraint. So that condition number of degrees of freedom has been reduced. And number two is the coordinates has to be linear, have to be independent. So these two things are important. One is these are minimum number of coordinates, general coordinates. Number one. Number two, the coordinates should be independent of each other. If any coordinate system fulfills these requirements, then we call this coordinate system to be minimum coordinate, called to be generalized coordinate. Now we have to consider two important principles in order to arrive at the Lagrange's famous Lagrange's equation. The principle, the one is principle of virtual work. First one is principle of virtual work. So we are considering principle of virtual work. Another thing that I will also discuss the principle of D'Alembert's. This is very important. D'Alembert's principle. This is D'Alembert's principle. These two principles has to be considered. Now, what is the principle of virtual work? Says that principle of virtual work says that if you have a system where net external force is Fi summation over I Fi, this is equal to 0. That is the system is in equilibrium. System is in equilibrium. System is in equilibrium. Then the work done for a virtual displacement. Then what is virtual displacement? Virtual displacement, since there is no force, external force, any displacement cannot happen due to this force because there is no force. So the displacement in which no work is involved is called virtual displacement. Right? Or in other words, in virtual displacement, we denote it generally by delta Ri, which is summation over I, delta Ri by del Q K, summation over K, delta. These QKs are generalized. QKs are generalized coordinate. learn it later. But the important about virtual displacement is that the work done due to this displacement is zero. So there are two ways to see this. One is that there is no force acting on the system. So work done will be zero. Another way is that the time is not involved there. Now this is very important. Why time is not? There is a displacement and time is not involved. If you say time is zero, then if there is a displacement and time is zero, then velocity will be. So that is a contradiction. Many standard books has committed has done this mistake by saying that the time interval between the particle is zero, which is nonsense. Nothing. Time interval is not there, zero, but time is not involved here. That means this displace this displacement um, has not arise due to the action of forces. So this displacement called virtual displacement. In other words, or in simple, if the net force is zero or the system is equilibrium, then then this displacement called virtual displacement. Right? So in virtual displacement, you will see that time is not involved. Actually for general displacement, there will be del Ri by del T into delta T. But for virtual displacement, this term will be zero. Del Ri del T equal to zero because delta Ri is not changing. Time is not involved, but not time equal to right? So if there is a system in equilibrium, the forces are in equilibrium, then virtual work is zero. That means if I write if I dot of delta I, both as vector sign, summation over I, then this is equal to zero. This is called principle of virtual. So total work done due to virtual displacement on a system of particle in equilibrium will be zero. So the principle of virtual work can be stated that I'm saying it very slowly so that you can copy it. The virtual principle of virtual work states that the work done due to virtual displacement of a system which is in equilibrium is zero. And this is called principle of total work done. Total work done due to virtual displacement of a system in equilibrium is zero. This is called principle of virtual work. Right, you got the point. Now, as I have mentioned before, in the applied forces, two types of forces are there. I'm sorry, applied forces, two type of forces are there. One is external force, F external, and other is F constant. I call it F constant. Right? The forces are two types: forces of constraint and forces of external. And these two forces, action of these two forces, may have equilibrium. Right? Dot of delta Ri equals to zero. Now, if we consider the system for which force of constraint work done due to force of constraint F dot of delta Ri, I think there will be a suffix I for each. So if I external will be there. If I external and if I. If I. So if I dot of delta Ri summation over I, this will be equal to zero, right? Because force of constraints do not do anything. Then this equation can be written in this form. Principle of virtual work can be stated. If external is a suffix I dot of delta Ri. So this is called principle of virtual work. Right? The principle of virtual work is initially contained in force of constant. Now, in the revised form of virtual work, The external force is only considered. Let us give an example so that it will be clear. Otherwise, things will go over your head. Let us take a classic example of equilibrium. Suppose this bob is in equilibrium under the action of three forces. One is F acting horizontally, another is T tension on the rope, and the force mg is acting downwards. So under the action of these three forces, the system is in equilibrium. Right? Then what we can say that principle of virtual work says that summation over I initially Fi dot of delta I equals to 0. Since here the number of particle is 1, so for sake of simplicity, so we can write this thing F dot of, I'm sorry, I am giving a dash, dash, delta R, delta, I'm sorry, delta R equals to 0. Now here three forces are there. One is T, right? Vector T plus vector A plus mg giving a vector say g cap. G cap is the direction. Dot of delta 0. Now, if you displace this thing, since the length between force of constant is this, the length is constant. So, if it is moved, it is moving, and displacement will be perpendicular. Very simple. Delta R should be perpendicular to T because this force, this length cannot be varied, right? So now T dot of delta R would be 0 because T is the force of constant, right? T dot of delta R would be 0. So the equation should be F plus mg g cap, right? Mg g cap dot of delta I'm giving it a vector direction because it is in this direction. This is equal to 0. So the principle of virtual work says that there are two forces, external forces. One is force applied, and another is force due to gravity. This two summation of the two forces are applied force. So virtual displacement under this axiom is zero. Now from this equation, you can find a relation between F and M. Do a little bit, find a relation. I am giving it as homework. This is right. Homework. Suppose this angle is theta. Suppose this angle is theta. Suppose this angle is theta. So find homework. Find the relation between F and G. F and find it. Or simply find it. Find it. In terms of course, it will be in terms of G. Right? So using the principle of virtual work, it will be this. Now you can check with your class 12, class 11 knowledge that you can decompose this force. Total three forces are there. So you decompose this force into this component. This is one component, and this is another component. So this will be T cos theta, and this will be T sin theta. Right? So if we get T sin theta and we will T cos theta, at once we get the relation between F and G. But do the homework for not considering T cos theta, T sin theta, considering F and G and this relation. F dot of delta will be what? How much? So you have to find the angle between F and delta. and the angle between mg plus delta and delta, right? Mg, if you find this angle, then this angle is 90 degree plus this thing, then it is sort of actually the same relation. Yeah, right. So we are there. So I guess you have understood the principle of virtual work. Now, for a static problem, right? What we are considering the static problem. Static problem. System is in equilibrium. Now, static problem আমরা করেছি। Dynamic problem কি এটা apply করা যাবে? Can we apply this thing to dynamic problem? That appears absurd. That a static problem, how can we apply it for a dynamic problem? Because for a static problem, we know that time is not involved because it is static. So whatever be the time, it is not changing. That's what static means. Can we apply this principle to dynamic problem? So common sense says, or most of the people, 1 in million, say million people, one except 1 in million people will say that no, it is not possible. But the genius like D'Alembert considered this. What he considered is that when a force is applying to a body, the body will move with an acceleration. So there will be reverse effective force, and that reverse effective force with the force will be in equilibrium. Right? So I am now considering the D'Alembert's principle. So I am considering now D'Alembert's principle. What he did, what he did is that for a dynamic problem, he made it static. Dynamic problem was made static problem by the inclusion of the term reverse effective force. Reverse effective force. What is that? Suppose I am considering force with Newton's second law is force equal to dp right? So I write it P dot F equal to P dot. Now F minus P dot is equals to 0. So these are two forces. One is the applied force, and this force minus P dot is called reverse effective force. Reverse effective. Let me illustrate. Suppose you are applying a force to a ball. The ball will accelerate, right? Now, in order to apply the force continuously to the ball, you have to move with the ball. Is it clear? Otherwise, you cannot apply the force. So, the contact between your, say you are applying force by your hand. So, contact between your hand and the ball is same, right? There cannot be a separation between hand and the ball. If there is a separation, then you cannot apply the force. So, in the frame of the ball, you see that the ball and the hand is in equilibrium. So there is a reverse effective force, right? So by introducing the idea of reverse effective force, the system is in equilibrium, right? Now considering the system where the applied force is also included into the moving system, then forces are in equilibrium. Then we can apply principle of virtual work. Now applying principle of virtual work to this, we can say that suppose this is for a particle I. Then applying principle of virtual work, we can say that Fi minus Ei